Afternoon. I'm Rusiru, a fourth year undergraduate of BSc in Software Engineering offered by University of Central Lancashire at Universal College, Lanka. So today I'm here to present our research on masked RCNN for Sinhala Sign Language to text conversion. The co-author of this research is Mr. Tepul Ginike, a senior lecturer and a program coordinator at Universal College, Lanka. So this will be the plan for my presentation today. First, I will give an introduction of our research. Then I will explain about the objectives, the methodology, the results and discussion, and finally the conclusion and the acknowledgement. Our research is based on Sinhala Sign Language interpretation that mainly focuses on the Sri Lankan population. Sign language is a form of communication used by disabled people with difficulties in communication due to their speech and hearing impediments. It is mainly used by the deaf or mute population where they use various gestures. In order to ensure an effective communication between people, a common method should be available. Unfortunately, this is not practiced. Therefore, a huge communication gap is found between sign users and natural language speakers like us, since we have no knowledge of sign language. As a result, people with speech and hearing impediments face many challenges in the society. The main reason for selecting this as my research topic is this communication gap between sign language users and natural language speakers. In 2020, it was stated by the World Federation of Deaf that there are around 72 million people worldwide who use a sign language for communication. Then World Health Organization has also revealed that over 5% of the world population, which is around 430 million people, require rehabilitation to address their disabling hearing loss. In Sri Lanka, we use Sinhala or Sri Lankan Sign Language, which is the native language in Sri Lanka. It was found that approximately 9% of the population has a loss of hearing in research that was conducted in 2019 by the WHO in Sri Lanka. So the main reasons for the communication gap are due to the lack of knowledge on sign language and the lack of sign language interpreters in Sri Lanka. In other research that was conducted in 2018, it was found that there are only 6 professional sign language interpreters in Sri Lanka. So there's a huge demand for interpreters at the moment. So there have been many research conducted on this topic, but they have not been properly implemented or are not being practiced. Another problem we found out in the previous research conducted was that most of the solutions consist of a hardware component where the user has to carry or wear a separate device. Due to this reason, I also have made my solution a mobile solution. The objectives of this research after conducting a literature review on previously conducted research are to implement a mobile solution to interpret Sinhala Sign Language, and by doing so, to reduce the communication gap between natural language speakers and sign language users in Sri Lanka. For the initial prototype of the system, a real-time sign interpretation feature and a Sinhala Sign Language dictionary feature were implemented. The first step of developing this system was gathering data. Since this research was based on Sinhala Sign Language, there were no proper data sets available. Therefore, by gathering few volunteers to perform the relevant signs, images of the signs were collected. A total of 200 images were collected for this purpose, and 15 signs were selected to prepare the dataset. The signs are displayed by this table. I have used numbers from 1 to 9 and 6 characters from the Sinhala alphabet, which is R, E, U, R, A, and E. After collecting the images, all the images were pre-processed and converted into TF records, which is the TensorFlow's binary format, which also increases the performance and the training speed of the model. The Label Me software was used to label the images as shown by the image display, and then the labeled images were converted into common object in context, which is the COCO format, and then into TF records using the libraries provided by the TensorFlow. Then the pre-trained model, which was used to train our custom model, was a mask RCNN Inception Reset V2, which was downloaded from the TensorFlow's model zoo. The structure of the mask RCNN model is shown by this image here. The reason for selecting a pre-trained model is because it is previously trained using a large-scale image classification task. Therefore, it has a higher accuracy after even customizing. We have used transfer learning to customize our model to our requirement. So we had to use Google Colab due to lack of resources like a GPU to train the model with the virtual GPU available. This image shows the loss curves generated by the TensorBoard. By analyzing the loss curves from these graphs while the model was training, the training was stopped when the graph curves started to flatten, making small differences in the loss values. This was done to prevent the model from overfitting and to get the lowest loss value from the model. This diagram shows the flow of the features of our system. For the real-time interpretation, we have implemented two features as the live interpretation and the video interpretation. The user is first given the option to select either one of these two features. If the user selects the video interpretation, he or she is given the option to upload a signing video to the system. After uploading the video, it is sent through a frame separation module where each frame of the module is separated and then pre-processed. If the user selects live interpretation, he or she is allowed to capture a live video from a signing person in front of him or her. This does not go through a frame separation since the video itself is captured as frames. Therefore, while the video is being captured, each frame is pre-processed. After the frames are pre-processed, in both the features, the frames are sent through the model to run inference, which will detect the sign in that specific frame. After detecting the sign, it will return an output label, which is the index of the detected sign. And by using this index, the text value is retrieved from the MySQL database, which stores the relationship between the index and the text value of the sign. Finally, the retrieved text is displayed to the user as the interpreted text. This figure shows the technologies used to implement this system. We have followed the 3D architecture to implement the system. It consists of the presentation layer, which is the mobile application that was developed using the INIT framework. The reason for selecting INIT framework was that it's a cross-platform technology which allows to easily deploy the application to any platform, either mobile or web. Then there is the logic there where the interpretation occurs. It was developed using a Python class framework. This also consists of the TensorFlow model, which was previously trained. And we have used the Jupyter Notebook to perform the pre-processing of the model. Finally, there's the data tier, which stores all the data needed to run the application. This consists of the MySQL database and the TensorFlow's GitHub repository, which was used to download the model files. And also it contains the trained model. Google Cloud was the client server that will be used to host the backend API of the system. In this case, the presentation layer, which is the mobile application, is used to feed the data into the system, while the logic layer, which is the backend API, is used to perform the functions of the system using the data available in the data layer. Now I will play a small video to show how the system runs. For this demonstration, I have deployed the application as a web application. So this is the live interpretation feature. The user is given the option to open the camera. Once the user clicks on the open camera button, it will open the camera view as a web view. So the characters I have used for the demonstration are number 5 and R and E from the Sinhala alphabet. So once the user clicks on the start button, it will start the recording and interpretation of the live video. First, number 5 is used. The next letter, it is R from the Sinhala alphabet. As you can see on the screen, it already displayed the interpreted value of the character I have used, which is number 5. Now the second character is displayed here, which is R. And finally, the character is displayed like this. So this will go as a cycle until the user clicks on stop or closes the application. So the next feature is the video interpretation. In this case, the user is given the option to upload a signing video from his or her device. So as you can see now, the video is uploaded to the mobile application. So once the user clicks on the tick icon, it will be sent to the backend of the system, and the processing of the video will start. In this case, as I explained before, the video is separated into frames and processed, and the output generated is displayed here as shown. The final feature is the Sinhala sign dictionary. It will display a list of signs from the Sinhala sign language. This is to create awareness and spread knowledge on Sinhala sign language. Currently, since we have used 15 characters, we have only displayed 15 characters and their respective signs. As a short from the video, for the initial prototype, we have developed 3 features: live interpretation, video interpretation, and finally the sign dictionary. These 3 images shows the user interfaces of these 3 features. By conducting relevant tests, we have calculated the average accuracies of each sign used in the current version and are displayed by this table here. By using these values, we have calculated the total average of the accuracy of the system to be as 77.8%. So by conducting the relevant test, we have also identified a few weaknesses of our system. So the first weakness was that the accuracy of the interpretation depends on the light conditions of the captured video or the uploaded video. Next is that the current prototype only works for static signs. It does not work for dynamic signs. Also, due to the lack of resources, interpretation took longer than expected in the live interpretation feature. And it could not be deployed in a mobile device since it requires a high performance. So currently there is no method to identify whether a frame contains a sign or not. Therefore, each frame is detected as a sign itself. So for the future enhancements, we hope to improve the accuracy based on the light conditions by feeding more images into the data set while training the model with varying light conditions. And we hope to deploy the live interpretation feature on a mobile device by using more resources to the backend. Then by training the model with more images, the speed of the interpretation can also be increased. And we hope to implement a dynamic sign interpretation module so that it is a complete sign language interpretation system. And finally, we also hope to implement the sign detection module for the frames so that only the frames which have signs will be detected by the model. As a conclusion, the challenges we have faced during the implementation of the system were a lack of resources mainly, such as a high performance GPU and RAM. Another was that since the system mainly focused on Sinhala sign language, there were no proper data sets available specifically for Sinhala sign language. Therefore, we had to create new data sets for this purpose. Despite the challenges faced, we were able to successfully implement the interpretation and other features. We were also able to get more experience and knowledge on machine learning techniques and Sinhala sign language by doing this research. Finally, we hope our solution will be able to reduce the communication gap between sign language users and natural language speakers in Sri Lanka. Now I would like to we would like to extend our gratitude towards our parent university, which is University of Central Lancashire and Universal College Lanka, for helping us throughout this research, and our colleagues for always motivating us and guiding us through throughout this research, and also finally the staff of MLNP for giving us this opportunity. That's it for my presentation. Thank you. Any question?